Ah, yes, there was an email. I don't know yet. Uh, so there is colloquium before the exam. So where you have to reproduce proofs, and then there is and during the exam there is problems. So the exam with so it's explained on the wiki.
Before the winter exam.
Yeah, in December.
Yeah, I meant like this exam week, like
On
it
the
starts
next week.
on Friday,
Ah, no, nothing.
so we don't have to submit our homework, or
Well, the regular homework, but I think it's after the session,
okay.
so you can go on holiday. Okay, last lecture, I forgot about the quiz.
Don't worry.
Today I have a quiz from previous year. So I just need to find the file. Okay. So now the recording is switched on. There are 3 students. But I only have blue markers. The black one is bad. Yeah. No. Bad.
One more try.
Yeah.
You will success.
Yeah, so it will be blue markers. Okay, so this lecture we speak about, so previous lecture was about realizable setting. So it means that we have a hypothesis class H, and for training and testing, we use a function from this class H. So to assign labels for training and testing. But of course, we don't know which function H and which function from H, and we have to figure it out. Or at least, well, we don't need to point to a function of H, but just any function is good, but we are confident that at least one function works. Now we drop this assumption. So there can be 2 reasons why we do not take labels from some function, the hypothesis class H. So there, it can happen. There are situations where a true function exists, but it's very complicated. And so, like humans, they can easily distinguish. Suppose we have few data, and we want to distinguish cats and dogs, and humans can do it easily. But if we only have few data, a neural network needs to learn too much if we don't have any pre-trained weights or something like this. So the task might be too difficult. Second reason is true function might not exist. So, for example, you have to classify paintings. There is a street where people walk by, and so they say ugly or beautiful when you show them some painting in some window for just application, and then you want to predict in advance, see the passenger, if he male, female, and big, age, and so on. So what will he say? But then the same picture, somebody might find it beautiful, somebody might find it ugly. No, let's say that we just show different pictures, and then we think whether the next passenger will find it beautiful or ugly. And but then the same picture, some people might find it beautiful, some might find it ugly. So in this case, there is no true function. So there are like 2 types of difficulties. and they are treated in the same way. But we will speak a little bit about risk decomposition. So the two types of problem contribute both to the risk. And so we can actually decompose it. So that's what we will do in this lecture. And then we will prove, so we will speak about bias complexity trade-off for finite hypothesis class. And then we will copy the nice bound for VC dimension. So we will speak about agnostic sample complexity and then prove a bound using VC dimension. So these are the three goals for today's lecture. So in the notes, there is a little example. Oh, mixing a little bit. Okay, so now, well, so now classification task. Before there was a true function and a probability measure over inputs. Now we have a probability measure over input-output pairs. For the track. So we have P over X times Y. So remember, Y contains two elements, and X can be any non-empty set. And so so let us first define what might be an optimal classifier if we have such a measure. And so our goal is to come up with a mapping from inputs and outputs and what can be an optimal. So let's do a little example. Let's have three inputs. Okay, I will call them x0 and +1, and then here we have two labels. So let's call them positive and negative. And so I'm a bit funny with in the notes. So let us have a distribution like this, 1/5, and then 1/5, and so what is the mapping from X to Y? That creates the smallest amount of error according to this measure. And so here we have a measure P over input-output pairs. So three inputs, two outputs. So the sum 1 + 1 + 1 and 2 is 1. So best classifier will and so we'll first predict positive here and then negative on the other two ones. Okay, let's flip the labels. Then we have a threshold classifier. Here negative and here. Okay, so then okay, so the optimal X is equal to positive bigger than 0 and negative otherwise. Okay. So the here, so the first thing that is let's define the risk. So now realize I should change the order because I speak about measure concentration. Okay, so risk RP of a function f is equal to a probability when we generate inputs from P. So it risk depends on a measure and it's just probability that f misclassifies, which is something quite unique. Okay. And now our plan is to decompose the risk of a classifier, of a learned classifier into three components. So first component is irreducible risk, and this only depends on the measure we are given. It's the minimal risk of a classifier. So irreducible risk is equal to minimum of RPF. So for all F. Right. So in our example, what is irreducible risk? So here, irreducible risk, what is it?
1/5.
1/5 indeed, because here our classifier is correct, and the best choice or the last input we take is to use plus, but then there is 1/5 probability. Okay, so the bias optimal classifier is a classifier that always pick a label that has maximal a posteriori conditional probability. And so for each x, so F is bias optimal. If don't is the probability of x, so it is conditional to the input being x. Yeah, I will just write x. So when we take okay, and now so this is first component, irreducible risk. So second, when we learn a classifier, so we will of course generate the set X, the set S, by sampling n elements and pairs from P independently. So S is equal to X1, Y, and now I use S for a label training set. X and Y n. And the learner output as usual F of X, X, Y. And so we are interested in the risk RP of F of X. So that's what we want to understand, what we want to know. And we want to compare this. So given the hypothesis class H, then we want our learner to output a hypothesis that's close to the best hypothesis in H. So the goal is to have RP of SS that's smaller than minimum, or let's say infimum of RF. Plus some small epsilon. Okay. So the next thing is that it can happen that H, for example, H might be a set of linear threshold functions. And there might be some linear threshold function that's very close to a bias optimal function. So, and in this case, the difference between the best function in H and the risk of the best function in H and the bias optimal, bias optimal function is called the bias of the risk. But I mean, it is the word, so the bias, bias of H. So it's nothing to do with bias here. I mean, the definition, I mean, etymologically, bias, you understand the word. So bias of H, it is defined as the minimum risk of a classifier in H minus irreducible risk.
Can I ask?
Yeah.
So we have like f from S, and we have also H, and we want to find like the closest function in H. That's that like.
Yeah. So we want to be as good as the best function in H. That's our goal.
Okay.
And now I'm discussing about two types of errors that we will need to deal with. First one is irreducible risk, and it corresponds to the situation where there is no perfect, where there is no true function. Like here, we can have both labels. So there is no true function. That means there is non-zero irreducible risk. But also, our models might be too easy for the real task. And that might be another reason why we make mistakes. And this is expressed by the bias of H. And it's just a difference between the best risk of a classifier in H and the irreducible risk. And so if I make a picture, so we might have 0 and then 1, let's say 1/2. It doesn't matter. And so we might have here irreducible risk. R on F star. So the bias optimal risk. And then we have minus RB of that's an H. And so this difference is bias. And then there is a last part. So here is the risk of our learned classifier. And this is called estimation error. So these are is the decomposition of risk. So let us change a little bit. So imagine that here we have 1/10 and 3/10 and 1/10. No. Yeah. So imagine we are learning, here is an example, we're learning threshold classifiers. So here H is equal, you remember threshold classifiers, should I write? So we predict positive when we are above the threshold. So what will, so here we already, so in this example, irreducible risk is 1/10. Right? So the best classifier will make 10% error. Then next question, what is the bias in this example? So we have to check the best threshold classifier. So when we start to predict positive here, for example, our error will be 3/10. So when we predict positive here, okay, this is worse error. So when we always predict positive, then error will be 3/10. Yeah, error will be 3/10. So the best we can have here in our example is 310 here, 110 here, and so the bias is 210s. The
Can you
difference.
explain please, if we always predict positive, why is there 3 times?
So if we always predict positive, the error is 310s. It's the same as if we predict a positive starting from here. Okay, so maybe I should take 1/5, 110 here. So if we start to predict positive from here, then what is the error? It is 1/5. And if we predict always positive, error is also 1. Okay, it doesn't matter. So now I change the example, and the best prediction is 2/10, 1/5, right? So it doesn't matter if we take if we take all positive now, then the error is sorry, all negative, then the error is 3/10, which is worse. So the best is to select positive from here. So our threshold classifier.
Can you please explain what is?
Oh, sorry, the sound is not loud enough. Yes.
Can you please explain what is in the cells of the table you
Yeah. So here is probability over input output pairs.
and why doesn't it adapt to 1 if it is probability?
Oh, sorry, I made a mistake. Yeah, good question. So yeah, let's. So this was a bad probability. Okay. Let's have. Okay, now we have a new example. Now it's
Okay.
not convincing example. If I stick 2/5 here and 1/5. Okay, so now it adds to 1. Thank you.
Yeah. So it is the probability of the pair that is on the cross section being given while training.
Yeah.
Right. Yeah. Okay. Thank you.
Well, there is no training set in our example.
Then can you please state what like the probability of what is this?
Yeah, this is an input distribution over pairs X and Y, but I didn't formalize a training set.
Oh,
So-
okay. Thank you.
Yeah,
So now it is the best strategy is to always predict negative class.
yeah, indeed, yeah, okay, yeah. So to put the threshold to the right. Okay. So this is our example. So now let us define the sample complexity. So sample complexity is related to our goal here. So as usual, there are 2 parameters. And sample complexity is minimal number at minimal n that we need. So the agnostic sample complexity has the same parameters epsilon and delta is equal to minimal size n of training set such that there exists a learning algorithm that with probability 1 minus delta. So delta is the error that we have bad learning. Output satisfies this condition. So this is definition of agnostic sample complexity for a hypothesis class H. So epsilon is how close we want to be to the optimal classifier in the class. And delta is probability yeah, over generating the training set over S from P to the power N. And this is for every P. So it doesn't, so worst case over P. So there exists a learning algorithm. For every P over X times Y. With probability 1 minus delta over S from Pn. So the learner outputs hypothesis class F of classifier F of S that satisfies this inequality. So there should be exist one learner that works for all measures P, so that with probability 1 minus delta over S from P, this condition is satisfied. Okay, and so a first observation is that it must be bigger than the deterministic sample complexity. I mean the sample complexity in the realizable setting. Okay, so why is it true? Well, agnostic setting is kind of special case for realizable setting. So let us try to remember what we had in the realizable setting. So there, a classification task. Yeah.
There is a written the same thing.
Sorry, yeah. Agnostic setting. So remember how we defined risk in the realizable setting. So there we looked at, we had a probability P over X, let's call it P tilde over X, and we had a true classifier that's mapping X's to Y's. And then we defined the risk for the function F in a certain way. So, so here we have, oh, I deleted it, this was not clever. So here we have RF equal to probability when we pick X, Y, sorry, when we pick X, when we pick X, Y from P, probability that F of X is not equal to Y. And then in the realizable setting, we were interested when we pick X from P tilde, probability that F of X differs from H of X. And this is basically the same thing. So given P tilde, we can create a problem P that is very similar. We concentrate all the labels in according to the true function. And so we say that P of xy, the measure for seeing the point xy, just is equal to well, it's equal to two cases. So if y equals the value of h, then we have P tilde on the point x, and otherwise we have 0.
Are we still in the realizable setting?
So here P tilde is realizable setting, and what I'm doing now is I compare risk in realizable setting. So sorry, this is what we cared about in the what we use for defining sample complexity. We said that we have successful learning in the realizable definition if this value was smaller than epsilon. And it needed to happen with probability 1 minus delta over generating the training set. So this is what we discussed previous week. But now, in realizable setting, I'm explaining that realizable setting is a special case of this setting here, where we have a distribution, because each task P tilde H corresponds to a measure P. And if we use such a measure constructed in this way, then this infimum will be zero. And because when we choose f to be the true function, this infimum is always right with probability 1. And so having risk satisfying this condition is just having this risk, having this condition satisfied. And so in the agnostic setting, we need to satisfy more conditions because we have more p's here. And in a realizable setting, there was P over marginal distributions and true classifiers here. Okay. So our task is harder, and that's why we need a bigger training set. Yes. What else should I say? I think that's it for first part. I need okay, for second part, I will first say a few words about measure concentration. So our goal, so now I will speak in implicit way about agnostic sample complexity, but I will more speak about agnostic sample complexity. It's not used very much. People will rather make bounds for the risk. Because you want, so this is a measure for error on test set of machine learning algorithm. And people want this to go down very quickly when the training size is increased. So people are more interested in this. Yeah, and I will speak about it for finite age. And then in the end of the lecture, we discuss what happens for infinite age. So if we learn threshold classifier with the real parameter. And so then we will see that agnostic sample complexity. And so before, for a realizable setting, we had the bound 1 over epsilon. And then some VC dimension of H plus ln 1 over delta. And we proved a little weaker bound. For agnostic setting, so this is realizable. And for agnostic setting, we get something similar, but we have up to constant factor from Haneke theorem. Here we will have very similar, but there will be 1 over epsilon squared, and here we will have the factor log 1 over epsilon here. So it's necessary here. And okay. Oh, wait, actually, sorry, it's not necessary. I think there exists also different, sorry, there is a different proof without log 1 over epsilon, but we will prove it with the 1 over epsilon. Okay, so this is what we will be doing in the lecture. But first, let us speak about, so we don't need this definition anymore, because we will speak about risk bounds. Okay. So, but what we will use, so maybe you learned about Chernoff bound and Hoeffding bound if you had statistics course. So let's quickly repeat this. So their measured concentration result, we will need to have slightly general than Hoeffding bound. So last year there were a few people who learned about Azuma theorem in another course of bounded difference inequality. So, but let's just repeat. For now, let's repeat what is measure concentration. So concentration inequality is a bound that says that a random variable is somehow close to its expected value. So bigger than t is small. Or opposite e to the expectation minus x bigger than t is small. It's concentration measure, and they are all you. So the grandfather of all measured concentration inequalities is Markov bound. Probability that y bigger than s is smaller than expectation on y divided by x. This is for y with positive support. So it's Markov there. And then how to get Chernow bound from Markov bound. So you remember Chernow bound. Sorry, Chebyshev bound. So how you get Chebyshev bound? It says that probability x minus exponent of x bigger than p is smaller than variance of x divided by t squared. Right. Okay. And so do you not remember how you get Chebyshev bound? By the way, Chebyshev is a Russian person who was in like invented everything in Tsar times. So it was very impressive. He was like way incredibly ahead. It's an amazing guy. So yeah. So I think this is from end of 1800s, like close to the year 1900. But I mean, it's just the beginning of what he already knew. So like he has like sub-Gaussian variables, which are now very famous, and he also has Chernow bound for sub-Gaussian. It's unbelievable. Okay, so Chebyshev, but how do you prove this thing?
We take the square of this inequality and we get
Yeah.
Markov.
Yeah, so our plan is to define a function. So function mapping reals to reals, and we set y. So there is a general technique. We set x minus expected value of x. And then we say that we apply, so we set y equal, we set y equal to f. And then in our case, we set f equal to the square function. And then we have probability that y equal to s. So we use monotone function, monotone increasing function for f, various monotone functions, and then we check that x minus e of x bigger than t is smaller than expectation f of x minus divided by f. So that's our plan. And when we take the square, we have precisely Chebyshev inequality. So, and you can do better, like say f of t equal to t to the power p. So yeah, Chebyshev inequality is actually okay. So you can have better inequalities when you take higher powers. So that is okay. Let us speak about weak law of large numbers. So how it's proven. Nice. So it says that if expected value exists, and then we take independent copies of this variable, then the average of these copies will converge to expected value. And so if x1 and xn are independent copies, variable, let's say x1 with finite expectation, then limit of 1/n. The value of equal to 0, and then this with probability 1, if I remember correctly. And so the proof, if also the variance of this variable is finite, well, I guess this was also in your statistics lecture. So variance of x1 is finite. Then we get this from Chebyshev inequality. Because the variance of, so let's call this x bar, so 1/n x1. Okay. So the variance of x bar, you remember? So what happens with the variance when we add up independent variables?
It's the sum, so we get 1/n times the.
Yeah. Variance of x1 divided by n. And what if we take a constant factor outside the variance? Then
Yeah, it's squared.
yeah, scale squared. So it is equal to n divided by n squared of variance of x1. So this is finite number. So the variance goes to 0. And so then we apply Chebyshev inequality, and we see that probability for the average to be larger than any positive number goes to 0. And so here we apply on this x bar. So for every finite value, if n becomes large, it goes to 0. And so with probability 1 means that if we take the limit for n to infinity, then this probability, this being bigger than epsilon goes to 0. Okay, maybe in the notes I should be more precise. I will update it, but it's like the formal details, like what means convergence and probability and so on. It's not so relevant for this course. Okay. So this is nice, but if we take f to be larger than the square, so this is all for Chebyshev, so if f is a square. But if variables are independent, we can even have faster convergence. So here we go, we have convergence by 1/n. And this is true, not even if we have fully independent, but if we have pairwise independence, then all of this proof will work. I mean, for finite variance. If the variance is not finite, then this is a harder proof. But for finite variance, we only use pairwise independent, but we can work harder and use this function and then obtain convergence that goes by n to the power. So you will have 1/n to the power p minus 1 if we use power p. and so on. And then there is an extreme case where we use exponent f of t equal to exponent of t. And this is proof of Hafting bound. So I will just write the statement because now we will use it many times. So I will just with constant rate. So I will just state a special case. So Z1 till Zn are independent. In 0, 1. So the real interval 0, 1. And we are interested in the sum of the variables. And then we have that probability that S bigger than expected value of S plus epsilon n is smaller than exponent minus 2 and epsilon squared. So in channel bound, we have the values 0 and 1, the binary values, and variables are identically distributed. So this Hafting bound is more general. So in fact, you have just arbitrary range, and in the exponent, you need to divide by sum of squares of the range. Well, you have n squared divided by sum of squares of the range. But for us, all the variables will be in 0, 1. So, so then the proof is for the homework because it's very important. And next lesson, we need to generalize it a little bit to prove. Okay. Well, the proof is for a little weaker bound. So where we don't have this factor 2, and then it's really short. So everyone has this question right for the homework. So, or at least most of the question. A few people maybe give up on one part. Okay, so this will be our friend for the rest of the lecture, is the Hafting bound. So now we will speak about uniform convergence. And for this, we consider empirical risk. So this is just the average. So if you're given a data set, then we have empirical risk of the training set of any classifier is just fraction of misclassified points. This 1 over xi not equal to yi. So as you remember, just n pairs xi, yi. And let us rewrite the risk. So note that Rp, we can write it as expected value of indicator function. So Rp of f is equal to expected value of f of x not equal to y when xy is taken from. And so I defined it as a probability. Probability if you randomly sample, but that's the same as expectation of indicator function. And so now we can understand that empirical risk. So it's called empirical means experiment. So it refers to the training set. Right? And so we know that for each function f, the true risk is equal to expected value of empirical risk. And because here, when we take expectation, just by linearity of expectation, because this is equal to expectation of sum.
Can you please repeat which one is the true and which one is an empirical?
Yeah, so this is true risk. And this is empirical.
Thank you.
So here we have a sum over I, but they are all identical. So we can just look to the first term, and this is the same as this here. Okay, this is a bit boring. But now we also know that this is an average of independent variables. So by having bound, it converges exponentially fast. So we have that. So let's think about the sample complexity. So there is a little lemma. This is, we will use it several times. It says that, so if we fix f, then with probability 1 minus delta, we have that empirical risk. I wrote it differently. So the true risk f is smaller than empirical risk of f plus square root 1 over delta over 2. Our lemma. And this we get directly from Channel dot. That we store it. So how do we get this? And so here is no epsilon, but there is a delta. It's a probability. So we set this equal to delta. And then we solve for epsilon. So if we then solve for epsilon, we will have ln1 over delta is equal to 2n epsilon squared. And so we bring this to the other side, square root, and we have precisely this thing. So this lemma is just having bound with little rearrangement. Okay. And so now let us think what happens if we replace f by the output of a trained classifier. So then we have some nonsense. And for example, imagine that we use H, the set of all classifiers. So our hypothesis is a set of all classifiers. And learning algorithm picks a set that is consistent with the training set. So this will be 0. And then if n is large enough, then the true risk of this learned. So what happens if we take the output of learned classifier here, and then we pick n large so that this is arbitrarily small, and then we see that generalization error on test set is 0 if we do this. But I did something that's not allowed. And because lemma says fix f, and then with probability 1 minus delta over S, I forgot to write it, but of Pn. And so with probability 1 minus delta over the training set, this result is true, but it's only for fixed S, f. It's not for an f that depends on the training set. So if we have some finite h, then we still can apply such a bound, but we have to apply it separately for each f inside the training set. So, so we can make a bound that doesn't work for a single f, but works for every f. But then we have to replace delta by delta over the size of f. Oh. So we have a lemma or corollary. With probability 1 minus delta over S from Pn for all F H, this bound holds. Our P of F is smaller than our head S plus, and then we have the square root, but now we need to have 1 over delta plus Ln size of H divided by 2F. And here we see a bias complexity trade-off. So imagine we want to train decision trees. So what do we want? So we want that the best decision tree has small error on training set. But if we take the complexity of the trees, so let's limit the number of nodes. And so let's say HK, decision trees with K nodes. If we take K big, then this will be small, but the size of H will grow linearly in K, as we've seen before. And so our bound is big. So there is again trade-off in the square root. And so if we take K here, then the first bound directly goes here, goes down. Our S of minimum F in HK, our S of F, but the square root bound will typically go up. Square root, well, this is the square root term. And so the sum will be something like this. Up here and then this is bound R. And so here we see that for the right complexity, the test error is optimal. So this is bias complexity trade-off. Okay, but here I'm actually applying this bound for a bunch of sets RHK. So we want to have this lemma, a version of this lemma that holds simultaneously for a sequence of classes HK. And so how can we, what's the idea? Let's assign a weight WK, for example, what K to K plus 1 to class HK. And then change delta to delta WK here in this bound. And so let me write the theorem. Okay, you will need to remember having bound. So please print in your memory for the rest of your life, at least for the rest of your studies. Okay. And if you do research for the rest of your life. Oh.
Can you please explain WK it equals to 1 by K?
Yeah. Okay.
Yeah.
It's very similar as we did for weighted majority vote. I will write a statement, prove it, and you will understand better. So I sketched the proof in words, but now it was a bit fast. So what
Sorry,
we
can
have,
you repeat what is K?
K, so here there was an example with decision trees of size with K nodes.
Okay.
So yeah, it's the set of classifiers from search decision tree. So let us write down lemma. So we have H1, H2, and so on. Sets of classifiers. And then I claim that the same thing with probability 1 minus delta over S of Bn. We have that this bound holds for all classifiers in any of these sets However, we need to correct this logarithm slightly. So this is our claim. So for all k, for all f in hk, we have that rp. Oh, and I forgot quantifier. Well, yeah, there is implicit for all p, all in the front. So it doesn't matter whether p is explicitly fixed or not. But let's not be distracted. It's rs of f plus, and then we have here the square root with a little bit more, 1 over 2n. So we have ln size of hk plus 2 log of k plus ln 2 over delta. So there's 2 changes. So we have this additional 2 log k and factor 2 over delta. So, and now let us, once we know the statement, it's much easier to understand it as usual. So now we have more uniform convergence. Okay, and so what's our plan? Let us fix these weights, wk, and apply for each class hk this lemma separately, but we replace delta by wk by delta. And so let me insert it. So here we have 1 over wk times delta with probability wk times delta. So something bad happens with probability at most wk, we have the opposite event. So something we don't happens with probability wk times delta. So now we need a union bound for all of k. So we need to bound the probability that there exists some k for which something bad happens. And now we apply the union bound. So probability there exists k for which lemma over lemma fails, and it is equal to w1 plus delta w2 plus, and this is equal to delta because the sum sum of wk equals 1. And so remember that wk is equal to 1 over k minus 1 over k plus 1. Okay, and now we just expand this. So we have ln 1 over wk is equal to ln k times k plus 1. And so it's equal to 2 times ln k. Well, so this is smaller than ln 2k k plus 2k squared. And now it's clear, right? So I can write ln. So the 2 comes from this 2. Okay. And this gives some cool bound. So there is a general principle called minimum description length principle. And so it's a way to bound the size of ln hk. And what does it say? So we have a set of classifiers and we want to prove that it's small. The technique is let's use a binary description of the classifier and bound the length of this binary description. And so imagine that all classifiers in HK can be described by f of k bits. So then we know that log of hk, the binary logarithm, is smaller than f of k. So this is technical. For example, when we have decision trees, we know that decision trees can be represented by a list of all the nodes on k nodes. And for every node, we need, so if there are decision trees on 0, 1, d, then every node is represented by log d plus 2 bits, and we need to do some rounding. So we take the seal. And so every tree in HK can be represented by this many bits. And so we set fk equal to this. And this is another way to say that HK is small. But decision trees are kind of simple, so we can do it directly. And we have the slightly better bound where we don't have this rounding for the logarithmic size. But if classifier is more complex, then this description length is a good way to bound this. And so now there is recent hype on neural networks to simplify the weights, and they come up with regularization function based on description lengths of weights. So I didn't read any of these papers yet. It's kind of suspicious because there are people inside big companies and startups, so they want to get money. Okay, yeah. So maybe it's interesting, but so this idea now is popular. So they even asked me to teach about Kolmogorov complexity, and then so such considerations are behind this theory.
Sorry, what is this letter?
The
K or
D,
R?
the dimension.
No, right.
K log.
In the middle, left. This one.
Yeah. So the same trees with K nodes.
Oh, it is K. Okay.
Yeah. So this. Yes, and now for the last 10 minutes, we have again the difficult proof. And I will not finish this, so you will have some reading. Okay, so now let's go back to our promised bound. So one can again say, look, this description length principle can always be applied because when I run some implementation on my laptop, every classifier has finite representation. But then, of course, you change the language, go from Python to C++, and your risk bound changes. It's nonsense. Then, and so we want the theory that works for infinite sets of classifiers. And so we can get bounds, risk bounds in terms of VC dimension. But now the risk bounds don't go down with 1 over n like before. The risk bound will go down by 1 over square root n, like similar to what we have here. And so things go down by square root over n, but they are proportional to the square root of VC dimension. So, okay, let me write the risk bound. Our next goal. Theorem, and this is by Vapnik and Chervonenko. So they knew about it in 1963, but then published in 1966 and 1967. So they're also Russian. But it was very good time in the end of 60s. But that's right, everything. So with probability 1 minus delta over S from En all F in H satisfy F smaller than empirical risk plus square root, and here we see that at 9 over 2n. The, of course, coefficients are not important. You see of H times ln 2n E over VC of H plus ln 1 over del, something with 4 over del. Okay, if it's readable, let's remove this thing because we don't need it there. Or over del. And the proof is similar as proof from previous lecture. So it goes into 2 steps, and then we insert bound on growth function, and there is some final calculation, but I don't care about this. So that gives these special constants. Okay, and so proof is as before. So first, we will consider a random splitting. So there is a first lemma that considers a set of length 2n. We split it randomly, and then we say that with high probability, each classifier in H will have on both sides equal number of mistakes. But now we need a little bit more quantitative version. So lambda is fixed U in of 2n inputs. And then the claim, U labeled set of 2n, and then probability when we randomly split. U in S and T, so 2 equal halves, and then probability that there exists some F in H such that empirical risk on T, empirical risk on our test set is significantly more than empirical risk on training set plus 2 epsilon. So this will satisfy channel bound. So this is first step. And then the second step, we'll say that when we have a good function and we generate a test set, we also have a function with low risk, or rather the opposite. So when we have bad function, or when we learn bad function, then it will make many mistakes on the test set. So probability n is bigger than 1 over 2 epsilon squared. So if we have enough labels, then probability when we draw a training set. So there exists H. Such that training error of F is much more than test error plus 2 epsilon. Oh, I really need an extra line. Is it visible? And yeah, is bounded by probability. No. Oh, why not? Let's write it on all of the probabilities as of T from Pn. So that's a probability on test set. And so we will estimate now. So what's our plan in this lemma? Let's replace this by error on test set so that we can apply this lemma. Probability, but then we consider slightly bigger bound because on our test set, this bound can be a little bit different. So we will use 3 epsilon here. Oh, and I forgot something important here. There is a growth function of the 2n. So exists F and H such that RE of F bigger than RS of F empirical risk plus 3 epsilon. And so now we can combine both lemmas. So then, let me write what is these two lemmas together. It says that probability there exists F such that bigger than our test of F plus 3 epsilon. Smaller than 2 times H of n exponent minus 2 times epsilon. So this is combination of these two when we take S from b to the power n. So the combination says that when we generate large training set, training error will be representative to test error with this probability. So that's once we have this, then we can derive bound on sample complexity agnostics, or we can derive this risk bound. And because it's saying training set is representative for test set. Okay, so now our job is to prove these two lemmas. Okay. So let's start with so this one is the easiest to prove, and so let's consider let's call it lemma 2. And then I need to write something. So I claim let's consider 2 indicator functions. So so in lemma 2 we have 2 sets S and T in the statement. So let us fix S. Fix S in X times Y to the power n. And so now let us consider, and so let us have f star be the function for which our p minus s. So what we need to bound here, we need to bound this probability, and we have fixed s. So let us look to the f for which this difference from left to right is maximal. So f star, so fix f star for which our p of f minus our s of f is maximal. And now let us consider some funny relational indicator functions. Our p of f star bigger than our s of f star plus 3 epsilon. So this indicator function I claimed is bigger than probability that our t of f star is bigger than, so probability for random t that this is bigger than our s of f star plus 2 epsilon. Okay, so let's look what is written and let's try to understand why it's true. So, so there is only one random thing here, that is the test set t. And we know that this, and we know that this thing here, so this is fixed. So we know that this is a random variable that satisfies everything bound. So we have exponential bound. But actually, Chebyshev is enough. Chebyshev bound, it will give us nicer things using our assumption here. N over 2 epsilon. So and so in order for this to be true, we need that. Okay, so there are two cases. Either this relation holds. Yeah, okay, let me think about the proof. So there are two cases. If this relation does not hold, then it's clearly true. If it does hold, so we know that empirical risk on S is significantly below the true risk, then probability that on the random set P, we are only a little bit below the empirical risk is small because we have extra gap. And so we know that the true risk is high. So what, very high, 3 epsilon. What is probability that this thing fails? So what is probability that this risk is small? So for this to be true, we need to be at least epsilon below the true risk of f star. And so we can bound this by Chebyshev inequality. And so probability that this fails, it is 1 minus, and so what we have here is variance of being wrong divided by n epsilon squared, because we have a step of epsilon. And so here is a variable variance of binary variable. Variance is always 1/4. So now, so this variance smaller than 1/4. But we also know something about n epsilon squared. It's bigger than 2. or bigger than 1/2, sorry. So an epsilon squared. So we have here something that's bigger than 1/4 divided by 1/2. So this thing must be smaller than 1 minus 1/4 divided by 1/2. So it is equal to 1/2. Okay, so now we understand what is this, and now to get the lemma, we just have to take, so here we fixed f, we just fixed s, we just have to apply it to random s, and then the lemma is proven. Oh, I'm teaching too long. So, yes. So shall we do quiz?
Maybe next time.
We don't have.
Okay, yeah, yeah. I will tell that the seminar will start a bit later. Oh, that I forgot about that. So now this thing is very similar as in previous lecture. So we fix, well, U is fixed. Then and to get from here to here, I didn't say clearly, right? So, but you understand, to take a random U for 2n by sampling 2n elements. So if that's true for each U, you take it's true for a random U, and then taking S from Pn and taking T from Pn is the same as taking U from P2n and randomly splitting. So you apply this for random U over 2Pn, and you have precisely the distribution here. Okay, I should stop speaking and then tell Nikita I only stop now. Okay. Yes. Early hour. Not so easy.